So today I just want to do a quick brief overview of what's called the completing the square technique, where it's essentially representing expressions as squares, usually minus a constant. Okay, and that has various applications, but I'm not going to go into that. Just a sort of uh, intuition check. Let's say we have the expression 2x squared minus 1. Okay, as is, we can't make this into a square of something as is, but suppose we add on 2x and subtract 2x over here. You can say these expressions are the same because we're subtracting the same thing we're adding, so we're just adding 0, right? And now you may recognize that this becomes x plus 1 squared minus 2x. So just sort of like geometrically, if our x squared minus 1 represents the area of some square. Okay, well, this whole expression, let's just say is a slightly bigger square, maybe a rectangle. And by subtracting the 2x here, we're essentially like cutting off a chunk, right? And what's left is this exact same thing. We're just representing it differently. In the end, it equals the same thing. Now, for practical purposes, I imagine you'd mostly see quadratics. So for a quadratic of form ax squared plus bx plus c, usually how it goes is, remember b divided by 2a squared. Because what this does is it's sort of like an easy out to completing a square. So usually how it goes is, given a quadratic of this form, you factor out this first constant there, if you want to call it that, and you're left with 2x plus bx divided by a. And we're only going to take out a for this part. We're going to leave our c over here. And now inside, we're going to invent some numbers, right? So similar to what we did before, we're going to subtract and add the same thing. So we're going to add b 2a squared minus b 2a squared plus c. Now, what this becomes is the square of x plus b over 2a. That's a complete square. And obviously we have to distribute the a, so this becomes a times that, and then minus a times this, plus our c. And similar to what we did here with the airs, again, this just represents a big square. We're removing a chunk, and maybe we're adding on a little with that c, and this equals the same expression than what we had originally, if we were to represent it as an air. But as a little sanity check, the world is not perfect. Maybe we're not going to be dealing with nice, clean quadratics, okay? Maybe we had um, x plus 1 over x, and we wanted to represent this as a complete square. Clearly that whole b divided by 2a squared thing is not going to really apply, or apply as easily. I'm not even going to try to do that. And what it takes a lot of the time is just some sort of intuition, right? So here we could sort of reverse engineer it. We could rewrite this as factoring out 1 over x to make this x squared plus 1 perhaps, and then adding and subtracting 2x to get this, completing the square inside with x plus 1 squared minus 2x, and then distributing everything out. And this represents the same thing that we started with. Usually what would happen is you need to you're usually using the complete square to find a minimum solution, right? So you're representing it as a new. Well, actually, this is a bad example because um, x plus 1 is always, or it doesn't have a x-intercept. It never equals 0. So this is the type of trial and error that you'll have to do, right? So instead, let's complete the square using the minus 2x. So we get minus 1 plus 2 here. And we're missing the plus 1 here. So finding for when this equals 0, we find that x is plus or minus 1. And when x is plus or minus 1, well, intuitively seeing y would be plus or minus 2. So that's our minimum value. And it's just a note to keep in mind that if stuff doesn't work out like this, you go back, you change whatever you want, you reverse engineer however you like, as long as it equals the same expression, so that you can find these complete squares that match your goals. That is the whole technique, right? Again, representing it geometrically as an error, we're just adding and subtracting the same thing. So it equals the same error, represents the same expression, just represented differently to meet our goals.